Alright, so we are group 1 and we did wire bonding and flip chip interconnect technologies. So we covered a number of topics on this one regarding wire bonding, flip chip, and also reliability. Under wire bonding, we covered intermetallic compounds for palladium coated copper wiring versus non-palladium coated. We talked about analysis of advantages and challenges for copper aluminum wire bonding over gold aluminum wire bonding. Then for flip chip, we talked about solder joint failures induced by electro and thermal migration, as well as a comparison of their driving forces, and also the effect of copper underbone metallization on current crowding. And for reliability, we talked about first level lead-free interconnect die, interlayer dielectrics cracking, and delamination. So for copper versus non-copper palladium coated, basically, as we move over to copper wire bonding, we use palladium to prevent oxidation, as oxidation can negatively affect the performance of the interconnect. And so, in addition, we also need to understand the copper aluminum intermetallic compounds as we move from gold to copper. So the researchers conducted EDS and TEM analysis of pure foreign copper wiring as well as palladium coated copper wiring. In the pure 4N copper wiring, they found that the atomic percentage of oxygen, so they found several layers in the TEM analysis. So both of them have a PT zone for FIB cutting. They have a zone B, which is mainly copper zone, but for the 4N, they had a copper aluminum oxygen intermetallic zone, whereas for zone D, whereas for the palladium coated, they did not have that. So the main takeaway from this is that the major compositions in the IMC layer after bonding aging process are CuAl2 and Cu9Al4. And then also for this, there shows that copper has diffused into zone D, whereas in the palladium coated, copper diffusion is minimized. And then also the percentage of oxygen is higher for spots in zone D closer to the IMC zone, but the gradient drastically decreases closer to the chip area. Now for palladium coated copper wiring, they were able to show that basically palladium itself does not diffuse throughout, and also palladium is effective in preventing oxidation and copper diffusion. They try to explain this by saying that palladium aluminum and copper aluminum have same mutual electronegativity, both less than gold aluminum, and so this mutual diffusion is unfavorable due to the low electronegativity and the high difference in binding energy due to the higher melting point of palladium. But they don't go in depth into the physics of how palladium prevents copper diffusion. And so when they were analyzing the bonding area, they found that there was a low percentage of copper aluminum oxygen microstructure in the bonding interface layer of a width of 3 to 4 nanometers, which proves that palladium is effective in preventing copper oxidation.
Hello everyone, I'll talk about the tests for copper wire compared with gold wire. On the left hand side, the figure shows a close-up image of the copper wire bound test vehicle. Notice that the kinks in the wire just above the ball bound that are typical of folded loops, which are used for low looming applications. On the right hand side, the top image shows parameter optimization range. There are 3 main parameters. The 3 main parameters of interest in first bond parameter optimization were belt force, ultrasonic power, and heat block temperature. Prior to bonding, the substrates were subjected to a direct plasma cleaning. The bottom image shows electrical test yields for gold and copper wires. Values for gold are set as the baseline. Copper yields are shown as relative to gold yield. We can see in this electrical test we got the better results in 3 of 4 tests and the close result in the last test. In the next page, the left image indicates wire pool results for each parameter set. Bonding temperature was 150 degrees centigrade. Points on the graph indicate average values for each data set. The average pull force value of gold wire is much lower than copper's. The right image indicates ball shear results for each parameter set. Bonding temperature was 150 degrees centigrade. Points on graph indicate average values for each data set. The dashed line indicates the average shear force value of gold wire. We can see under the conditions of same temperature, different sets of bond force applied and ultrasonic power, the copper wire can bear higher pull and shear force than gold wire. It proves copper wire has a much better mechanical property than gold wire.
In the solder joint, electromigration occurs due to the momentum exchange between diffusing atoms and flux of charge carriers moving in the direction opposite to the induced electric field. As shown on a picture, for a flip chip interconnect, a pair of solder joint is joined with aluminum thin film interconnect between the chip and the solder, and with copper line between the solder and the substrate. As shown in the picture, near the electron flux entrance point from an aluminum line, the current density is approximately 10 to the 5th angstroms per centimeter squared, while in the middle of the pump the average current density is 10 to the 4th angstroms per centimeter squared. This figure shows a scanning electron microscope image of SAG alloy, subjected to 1.8 angstrom current, stressed at 50 Celsius. As seen from the picture, void formation due to electromigration occurs only at the cathode end of the chip side, causing failure in only one of the two solder joints, not in every joint. Since most of electron flux enters the solder joint through a small area of the solder pump, the planar void propagation deflects the current entrance to the front of the void. When the void propagates through the entire joint, the contact becomes open, resulting in an open circuit failure. Thermomigration. Joule's heating is defined as energy dissipated by a conductor per unit time, where J squared rho energy dissipated per unit time per unit volume of the entire conductor. A rough estimate of Joule's heating per unit volume can be calculated as shown in Table 1. Infrared microscopy was utilized to confirm the hot spot temperature profile of eutectic tin silver solder joint with 150 micrometers diameter under applied current stress of 0.6 angstroms at 100 Celsius. As shown in a figure, a hotspot is located at the upper right corner marked by letter A. A temperature of a hotspot is about 162 Celsius, while a horizontal thermal gradient is 786 Celsius per centimeter, and a vertical thermal gradient is 2392 Celsius per centimeter, while a thermal gradient of about 1000 Celsius per centimeter is sufficient to achieve a silver atom migration. Thermal migration accelerates the void growth process and accommodates phase separation of silver and tin atoms, leading to the mechanical failure of flip chip solder joint.
In this slide, we will compare the thermomigration and electromigration driving forces. The electromigration and thermomigration driving forces are given by the following equation respectively. As we can see that F electromigration is basically driven by the parameter called current density, and the driving parameter for F thermomigration is temperature gradient. For electromigration in aluminium and copper interconnects, a current density greater than 10 to the power 5 to 10 to the power 6 ampere per centimeter square is typically required. This means that we need a temperature gradient larger than 10,000 degrees Celsius per centimeter to provide the same driving force, which is too high. Hence, thermomigration hasn't been a reliability concern in aluminium and copper interconnect technology. In the second slide, we will discuss the effect of copper under bump metallization on current crowding. The distant line to bump structure of flip chip solder joint is a key element for electromigration failure. To overcome this, copper under bump thickness can be increased, causing the crowding to occur in CU rather than in the solder. The given figure shows the effect of current crowding and its impact on the solder joint with UBM thickness equal to 10 μm. For this thickness, most of the crowding occurs in CU and only a small part of current crowding extends into the solder. Despite the nearly uniform current density, the void forms and grows larger with time at the current entrance of the bump. Furthermore, the void formation increases the Joule's heating, which induces a thermal gradient into the solder bump. Therefore, the EM, TM and Kirkcandle void formations are major concerns when copper UMB thickness is increased to reduce the solder current crowding effect.
The semiconductor industry's transition to lead-free necessitates the change to a low-K dielectric material, function of which is to insulate the dimetal layers to protect it from the environment. The change translates to improved IC performance through the reduction in the overall propagation delay. However, this created significant technical challenges to flip chip assembly and reliability due to the lead-free interconnect and low-K dielectric unique physical, mechanical, and metallurgical properties. The intrinsically high mechanical stiffness of lead-free solder creates additional stress to the die, causing ILD delamination and cracking. The lead-free solder high melting point is another concern, as it increases the CTE mismatch between the die and the substrate. The CTE mismatch causes tremendous stress on the FLI and the ILD underneath, which ultimately leads to ILD delamination and cracking. The images below on the left shows the mechanism behind the ILD delamination, while the image on the right shows a typical ILD delam cracking on a lead-free interconnect device. The flip chip packaging plays an important role in the silicon package interaction. Based on this study using FEA and Moray analysis, it was determined that the ILD stress is at its peak during the flip chip assembly process, particularly during the die attach. Table below shows the energy release rate of a lead-free package in comparison to a eutectic and high-lead solder package in the die attach process. It can be inferred here that the lead-free solder package has the highest energy release rate among the three types of FLI materials. On the other hand, the underfill process put the ILD stress to its lowest value. The simulation also validated that the lead-free solder bump ILD stress is about 25% higher than the eutectic solder. Finally, the study validated the impact of material selection, die size, and metal densities affect the ILD delamination and cracking mechanism.